Whether or not he said it, I don't know. But there is no force in the universe more powerful than compound interest. In other words, this is some pretty heavy stuff as far as the impact that it can have. Now, he wasn't just speaking about financial things, but we certainly are going to be speaking about financial things. We'll just start by writing down the formula that's in blue. We're going to talk about the formula that's in blue first. Okay? Now, the formula in blue is what's called our compound interest formula, and it's got several parameters that I have outlined over here in black on the right. My freshman on Friday when we were going through this told me, Coach Morgan, your handwriting is terrible. I can't read that. And so I'll do a little translating for you as need be. But we start with, instead of starting with A, I'm actually jumped down to the third one. We'll start with the letter P. Okay? So suppose I'm coming to Grove and I say, Grove, I've got some money I would like to invest with you. Okay? And like Grove is in this scenario is maybe either like a broker or he's somebody that works in finance that is going to take my money and use it to make more money, and then he's going to give me some back. All right, so I go to Grove and I say, Grove, I want to invest $1,000 in you. Okay, that's what P is. P is how much money I am investing, or I am depositing, or I am putting in. It's called the principal, and it's my initial investment. Okay, principal investment. I think I might have misspelled the word principal. It might be a P-L-E instead of P-A-L. P-A-L is the person. But anyway, you get the idea. So I go to Grove and I say, Grove, I'm going to invest $1,000. What can you do for me? And Grove is like, oh, okay, Coach Morgan, I'm pretty good with this finance stuff. I'll get you a rate of return of, let's say something ludicrous, like I'll get you a 12% rate of return on your investment. I'm like, oh man, that's amazing. Okay, Grove, that sounds too good to be true, right? But what that is that's the rate that he is saying that he'll pay me, okay, for my investment. Now, an interest rate is a percentage that when we do our calculation, I wrote DEC at the end of that. That stands for decimal. So make a note to that effect, that your interest rate, your R value, needs to be a decimal. Usually it will be quoted to you as a percentage, and we all know how to turn percents into decimals at this point in the game. Okay, so my 12% that Grove has quoted, Nate, that would be expressed as 0.12. Fabulous. Okay, now here's where we deviate from what you guys have learned about before. You've learned before about simple interest. Simple interest would be where Grove says, Coach Morgan, I'll give you 12%. And I say, great, here's my money. And I come back after a year and Grove says, here's $1,000 plus how much? Much of 1,000 is 12%. $120. And I say, thank you very much, Mr. Thompson. I appreciate the 12% interest that you paid me. That's simple interest. Okay. Compound interest works a little different. Okay, so like let's say that the Bank of Grove, instead of doing simple interest, is going to compound it. And let's say that they're going to compound it quarterly. Okay, so what that means is that he is going to take that 12% yearly interest rate and he is going to cut it up into quarters. He's going to cut it up into 4 parts. Okay. Now you might see why I chose 12%. What's a fourth of 12%? 3%. Fabulous. So the first quarter, which is 3 months of the year, right? The first quarter, he is going to compound the interest at 3%. Okay? So how much money is he going to pay me, or is he going to put into my account after those first 3 months? What's 3%? What's 3%? Okay, $30. And he's going to say, here you go, Coach Morgan, here's $30 of interest that you've earned. Now, the novice would say, well, that's stupid. Coach Morgan, you could have left it in there for a year in simple interest and got $120. That seems a lot better. Well, here's the rub. I'm not just getting $30 four times. I'm getting $30 that first quarter, and then what that $30 does is it earns interest during the second quarter. So now I'm earning interest on top of interest, or interest with the interest. So what would my next, and actually I'm gonna write this out because you guys know at this point I'm a visual learner. So like that first quarter, let's just say quarter one, I put in, here at the start, I put in 1,000 smackers. After the first quarter, what did y'all tell me I had? 1,030. Okay. So now during that second quarter, we're earning our yearly interest rate cut up into quarters, so our 3%. We're going to earn that not on $1,000, but on $1,030. Okay, and let me do a little quick calculation. 0.03 times 1030. Ooh, that's $30.90. So now I've got an extra 90 cents that I wouldn't have had otherwise. And then that goes in and that rolls in. And so after the third quarter, I'm earning interest on the interest from the first two quarters. So that you can start to see this sort of has like what's called a snowball effect. Okay, so like 0.03, not 0.03. That's what I want to do, plus 1,030.9. Now I've got $1,090. No, not $90, $91.83. $91 and about 83 cents. And then finally, after that first year, let's do it one more time. 0.03 times, actually, let's do 1.03. 1.03. Oh, don't, I keep, sorry, fellas, hold on. 0.03 times 1091.83. There we go. Bah, my calculator's messing up. Let me get my head wrapped around this. 1,030, 60, 90. So I should have, how much was it in our first example? How much interest did we earn in our first example? 120. So we should have more than, oh, okay, duh, I'm such a goober. After our fourth quarter, we're gonna have 1124 point, let's say 59. 59, thereabouts. So in this second little example right here, you guys can tell that I'm earning, about $4.60 more than I would have otherwise. Now that does not look like very much, does it? Okay, but let me draw you a little picture of what is happening here. Here's $1,000. And if we give it enough time, it will grow. How so? Use a good word from last week. It will grow exponentially. Okay? This is what we mean by exponential growth. It is a very powerful force because eventually it's going to start snowballing to the point at which our interest is earning so much interest on top of itself. All right, let's talk about another couple things. You know, Grove mentioned, or rather with my little example of him, I said, you know, hey, you're going to be compounding quarterly. Let's say that Luke comes to me and says, Coach Morgan, I will do you one better. I'll compound monthly. Okay, so instead of every 3 months waiting to get compound interest, I'll have to only wait 1 month. Okay, now that yearly interest rate that we're quoting here, that 12%, means now that Luke's in the game. Luke's not going to pay 3% per month. He's going to only pay 1% per month. But because he's compounding more frequently, what we'll see is that compounding effect will outweigh the quarterly amount. This is what N stands for. N stands for how many times a year are you willing to compound. So quarterly means N is 4. Monthly means N is 12. Daily would be 365, so on and so forth. Okay. Semi-annually would be twice a year. Okay. So those are some words that you'll see in the problems. T is how long we leave the money in the account. T is the duration of the experiment. So I might leave this money invested for, like 7 years, and T would therefore be 7. And the last thing to consider is A. A is how much money is in the account after everything is said and done. Okay, after we pull out and we say, okay, I want my money. How much do I have? That's what A is. Okay. So with that being said, y'all, you have any questions about the vocab? You have any questions about the blue formula? Okay. Let's work an example, and then we'll come back to the 2 green things right there. Okay. Let's see if we can get this. I might have to shrink this a little bit so we get. There we go. Come on now. There we go. All right. Example 4 says that we're depositing $1,000, and they're not going to pay nearly as much as Grove paid. They only pay 2.5% annual interest. It says find the balance after 3 years if the interest rate is compounded annually to start with. Okay. So here's my formula in blue. I'm going to say A equals P. All right. So Joey, what's my P value in this example? Yeah, $1,000 is my initial or my principal investment. So we got 1 plus R. George, how do I express my R value? Yeah. So the interest rate is 2.5%. So should I put 2.5 up here? Correct. Why not? Good. Convert that 2.5% into a decimal for me. Try again. .5% is not equal to 0.25. How much would 0.25 be? That'd be, Nate, help him out. How much of a percent is 0.25? That's 25%. So what could you do to your decimal, George, to convert it properly? Yeah, move it over to the left one more time, right? So in other words, 2.5% class is how much of a decimal? 0.025. So George and all, we move our decimal 2 places to the left to change it from a percent to an actual decimal. So we got 0.025. Now that's being compounded in part A here. This is our first little iteration. That's being compounded annually. Okay, so Charlie, what does that mean that my N value is? How many times per year do I do something when I do it annually? Good. So that's just going to be 1. And then it's raised to the NT, so that's going to be 1 again times. And we're leaving this in for how long, Jack Candiato? For 3 years. Good. Now, this is just literally a plug and chug kind of process on a calculator. Okay, that's why I got my calculator sitting up here. You don't have to have one with you today. I'll run those numbers for you. And actually, I've got an emulator. You guys can see the numbers getting run on here. Tiago, I see you got a hand up. I hope it hasn't been up for super long. What's up? What you got?
For some reason, it's taking a really long time for what you write to appear on my screen.
Paul and Lewis, are you guys having the same issue? Lewis is not. Paul is. Tiago, I'm sorry, dude. I don't know if there's a lag on our end. I don't quite know how to fix that issue. Are you guys seeing a lag up here, like big time, more than normal? Tiago, I am recording this, so if it is throwing you off too much, you could maybe watch the recording. Hopefully, it'll be a little bit better if you want to do it that way.
I'll just try to finish this. then I'll watch what it says on
Okay.
the record.
So like, do you see my calculator on the screen, and do you see that equation in blue?
Yes.
Okay, gotcha. So it's just off kilter by several seconds then.
Right.
All right. I'm sorry, dude. All right, so we're going to run the numbers. 1,000 is my principal investment times 1 plus 0.025. That's R divided by N. Close parentheses. The little exponent button right there is the caret. And then 1 times 3, I'll actually go ahead and do that multiplication in my head. And we get, what do y'all think? 89 cents. 1076.89. 1076.89. All right. Now that's part A. Part B, we're going to do the same thing, except we're going to adjust what? Alex, what are we going to adjust? What does part B tell me to do? Good. So we're going to adjust that N value. And like I said, I'll go ahead and multiply the exponent out. 3 years times 12 is going to be 36. So with my calculator now, I'm going to go back, and the only thing I'm going to change is dividing it by 12 and making it 36. Whoops, why did I hit graph? There we go, enter. So now we got 1077.80. 1077.80. Now, fellas, if all the things are the same, right, between these two, which one would you pick for your bank account? Why? You got more money, okay. The reason that you got more money was because it was being compounded more frequently. Okay, so part C here says, so let's try and do daily. So in this case, we're going to have 365. So 1 plus 0.025, our interest rate, divided by 365. And here I won't do that multiplication, bless you, in my head, because I don't know what 365 times 3 is off the top of my head. But again, all I got to do is hit second enter, and then change that to 365. And then change that to 360 as well. Whoops, what did I hit wrong? 1 plus 0.025 divided by 365. Oh, I was supposed to multiply by 3. That's an easy fix. 365 times 3. Now we're cooking. 1077.88. All right, so what you'll start to notice is that we jumped from 1 compounding period per year to 12 compounding periods per year, and we got like what, an extra buck almost, like an extra 91 cents, okay? And then we jumped from 12 compounding periods way on up to 365 compounding periods per year, and we only jumped up 8 cents. So there starts to be like this, I guess, depreciation of the impact. Like, what if I jumped up to 1,000,000 times per year, 1,000,000 compounding periods per year, 1,000,000,000 compounding periods per year? It's going to start to make less and less of an impact. Okay, so a couple of points to bring up. Number one, don't let, like, we're trying to be savvy consumers, right? Don't let someone advertise, well, hey, we'll compound monthly as opposed to quarterly, but then the monthly person pays you a smaller interest rate. Okay, we've got to run the numbers and be smart, savvy consumers on our own. So that's the first point. Don't necessarily just think that more compounding periods trumps everything else. It's a balance between what kind of interest rate I also get. Okay, and then the second thing is that these numbers are approaching something. They are approaching, like I just gave the examples of like 1,000,000 compounding periods, 1 billion compounding periods, 1 trillion compounding periods. they are approaching a particular value, a maximum possible value, which will run here in an extra special little example called continuously compounding interest. And that's that other formula that we had earlier. So e to the 0.025 times 3. Okay, the formula that we had up there earlier, and actually I'll go ahead and scroll to this formula right here. I call it the shampoo formula. Pert Plus is or it used to be a kind of a men's shampoo. P times e to the RT. Now E is an interesting number. E is about 2.71. You don't have to know this fancy definition of E. You'll get that later on when you guys take Algebra 2 or pre-calculus. But suffice it to say, it was developed by a guy named Leonard. Okay. Now, why do you think they named it E? Well, Leonard's last name was Euler. Okay, you're probably still thinking, why did they name it E? Euler starts with an E. It's E-U-L-E-R. So anyway, Leonard Euler developed this this notion of E, and you don't have, again, in Algebra 1, you don't have to know too much about it, but it's called the natural number. It's kind of like pi. You know, pi is about 3.14. Well, E is about 2.71. It's called the natural number, and it's got some interesting properties. But for our purposes, what we use it for in this case is when someone says we're going to compound continuously. In other words, we're not going to compound a finite number of times per year. We're going to compound every microsecond of every millionth, billionth, trillionth of a microsecond. In other words, we're continually compounding. Now, the whole idea behind that is that you're taking that interest rate and you're cutting it up into infinitely many pieces, but at the same time, you're compounding infinitely many times. So in blue is our basic normal compound interest formula. In green right here, circled with a red circle, is what's called compounding continuously. So if we see that phrase compounding continuously, we use the different formula. Here's what that formula would flesh out as far as our answer is concerned. And on my calculator, all I got to do is say 1,000 times and then e to the 0.025, that's my rate, times 3, that's my time, and I get just a hair bit more. I just get a little bit more. You can see the difference between the last example and this example isn't even a penny. It's like 3/10 of a penny. Okay, so there goes that idea of don't sacrifice interest rate for more compounding periods. There's my snipping tool. That's what I wanted. So the difference, fellas, between compounding daily and compounding continuously is negligible in this context. Okay, it's negligible in this context. That means it doesn't really matter because our answers, bless you, our answers are almost identical. And in fact, if we were going to round, they would round to the identical idea. Okay, so compound interest, very powerful force. When you're investing money, it earns interest, and then that interest earns interest. That's what we mean by compounding. All right, so any questions about what we've talked through so far today? All right, now we're going to jump into, actually, you know what we'll do? We'll work these questions to get the ball rolling, and probably we'll be out of time by the end of when y'all work these. All right, so there's 6 questions on the screen right here. Okay, and recently you and I have been talking about inverse functions. We're going to continue talking about inverse functions in this next lesson here in 10.3. So go through and find the inverse of each of these first 3 functions. The first one's linear, the second one's a square root function, the third one is a quadratic function. Remember your 2 steps for finding inverses. Switch x and y and solve for the new y. Okay? Switch x and y and solve for that new y. So like on number 1, instead of it being y equals 1/2 x minus 5. You're going to write x equals 1/2 y minus 5, and then you're going to get y by itself. Let's roll through that. We'll take about 2 or 3 minutes, and then we'll dismiss class for the day. Good. So wherever you see a y, put an x. Wherever you see an x, put a y. And then you use your inverse ops to get that new y by itself. Like on this first one, for example, I could add 5 to both sides. And then I could times both sides by 2. And so that's what my inverse would be. Will Edwards, what do you do on this number 2 when you've got x equals square root of y plus 5? What's your first step?
Take the square root of both sides.
Well, you already got a square root, so I don't want to take another square root.
It's a square.
Good, attaboy. We're going to square both sides. Because a square and a square root cancel each other out. Those are inverse ops. And then subtract 5 from both sides. Can we go ahead and do that?
Yes.
All right, so x squared minus 5. Fabulous. So that's what my inverse would be. So inverse equals x squared minus 5. Now, there's one small little caveat that I want to add in there. And if you guys remember, what does a function have to be in order for it to be invertible? What was that phrase where we said it has to be? You see my hand signal there? 1 to 1. Okay. Remember, in order for something to be invertible, it's got to be 1 to 1. It's got to pass the horizontal line test. Good. So can you tell me what kind of graph this f inverse, the answer that Will gave me, what kind of graph would that have? X squared minus 5, what's its shape? Yeah, it's a parabola. I'm not asking trick questions, right? That's a parabola. It's a quadratic function. It's a parabola. Now, is a parabola 1 to 1? In other words, does it pass a horizontal line test? Say no.
No.
So the problem here is that we've got an initial domain restriction that's implied on number 2. Okay, in other words, what kind of x values were we not allowed to have in this original? Like, what g of x is restricted to where, like, would -6 be a good input there? -6 plus 5 is -1. I can't have a negative radicand. So there are a couple of restrictions. I'll put them up here in orange. The domain restriction is that x has to be greater than or equal to -5, pardon me. What kind of range restriction do we have? Do you guys remember what the square root function looks like as far as its y values? Square root function right here, 1, 2, 3, 4, 5. It goes up and to the right. So y values are going to be greater than or equal to, yeah, good, Jack. Y is greater than or equal to 0. So here's my question, and we'll stop with this. Because I've got a domain and a range which are restricted, what can you tell me about the inverse function's domain and range accordingly? How is it restricted? You remember what we said last week? I walked around just now and kind of peeked. Some of y'all have some real good notes from last week. What do you know about the domain and the range of an inverse function? Where does it come from? The domain of our function becomes the range of our inverse function, and the range of our function becomes the domain of our inverse function. So in other words, there's a domain restriction that we have to put in place here. We got to say x has to be greater than or equal to 0. And the reason being is that if we were going to graph this out, right, we would only want the right-hand side of that parabola. Real quick, what line are they symmetrical about when we graph out a function and its inverse? Awkward silence. How about the line y equals x? Y'all are looking at me like, what are you even talking about this morning? We'll pick up with more of this tomorrow. No sweat it. Fellas, thank you guys for attending at home. I hope y'all enjoy a little bit of a late start today. And good luck to everyone with y'all's school day. And we'll leave it at this. Live Jesus in our hearts. Okay, thank you so much, guys. You don't have school tomorrow. Y'all got confirmation, right?